What's up? What's up? What's up? Went back into the lab again, busting out the trainer board to help me, and decided to use some Christmas lights here just to kind of show what's going on. Got my oscilloscope, and this one I'm using a solid state controller. This is off like a small exhaust fan or something where you can set the speed. So what this is going to be about is how this actually works. And what is it? So you can see the lights are at their brightest setting right now. Dim them, so that's fully dim right there. We'll go full bright. You can definitely see the light increasing and decreasing. Now on to the lesson. I have my oscilloscope, and you can see that, yes, I mean, obviously you all know that this is AC voltage, right? But that does not look like a sinusoidal wave. So what is it that we're looking at? Well, this solid state controller right here is a triac. And if you're not familiar with what a triac is, we can get into that, but it's just a way to control things, just another way of modulating. I don't want to call it a cheap way, but it's a less expensive way to do modulation. And again, so there's your waveform, and it's not sinusoidal. I will go here, and I gotta be careful because I am using mains voltage. Let's find something that would have a pure sine wave. Okay, so now I'm on just regular AC. Right there, that looks more like a pure sine wave, like what you're used to, what you'll see, 60 hertz. Now let's go back to the triac controller. So what are we seeing here? So this is kind of representative of what you would think of a sinusoidal wave would look like, right? But you see these choppy parts, and you see those little where they're shooting up right there. That is inrush current. So how does a triac work, right? A triac works by phase angle control, right? So watch when I start to lower it, what happens. You're seeing it shift, right? Which means that it's now, this is considered your zero crossing or 0 volts. And then all of a sudden it turns on. So imagine the sinusoidal wave, right? Down, up, down again. Well, what it's doing is it's only turning on the power at a certain part in the waveform. And it'll start to make sense a little bit more, hopefully, if I'm doing a good enough job. Right? We'll go full speed on or full power on this thing. So what is it doing? It's turning it on much sooner. See, you're turning on closer to the 0 volt line, which is called your zero crossing. When you turn it on later, like when the speed is lowered, in essence, you're just basically cutting the wave down which is what's known as phase angle control. Again, I'll lower it and you can see it shifting. So it's only turning it on at the top of the peak and then heading back down very quickly to the zero crossing. And you can watch as this happens. Now this is a downside to a triac. It generates a lot of heat and a lot of inrush current. Look right here. This is VPP, voltage peak to peak, right? You have peak voltage. There's your hertz. Get my hand out of there so it tries to focus. Right? The hertz will not change. You'll stay at 60 hertz on this. Your peak voltage would be from 0 up to the crest, which is 170 volts on a 120 volt. What your meter usually does is RMS, which is root mean squared, basically an average, right? So you have peak to peak voltage, you have peak voltage, and then you have RMS voltage. Now watch what happens when I slow this thing down. What happens to your peak to peak voltage? You will see a massive increase right there. Did you see how that voltage really jumped up? It jumped up to 500 and something volts. Which, sorry, my hand's all shaky here. I'm holding my phone, but I apologize for that. And as we increase the speed, your peak to peak voltage won't be as bad. And another downside to triac is the losses that happen. They are heat generating. They also generate a lot of RFI, radio frequency interference. You get these, it's happening at 120 hertz. Even though we use 60 hertz power, but 60 hertz, 60 hertz, 60 hertz, 60 hertz. It's happening at 120 hertz, so you do get a lot of radio frequency interference with these things. But this is the cool thing about an oscilloscope is you really get to see what the heck's going on. I mean, some of this may mean something to some of you guys, some of it may not. I mean, I'm a nerd for this stuff, so I just, whether it's going to help me or not is not really important to me. It's just fun to learn. And this is switching very, very fastly. We're talking nanoseconds. And yeah, again, that's a triac waveform. You hit your peak voltage, you go to zero crossing, it's off, and it starts conducting again. Same thing. You hit the zero crossing, it's off, then you get this large spike, and that's what that little line is you see right there. Those are the spikes. Because it's not a perfect controller. What would be better would be a FET or a MOSFET. That would be a better type controller, something with IGBTs like you see in VFDs. These are just less expensive ways to do it. They're obviously not the greatest, but you're also not paying the same price as you would for something that would have a more control. And yeah, these are just, triacs are phase angle controllers, and that using an oscilloscope, that makes a lot of sense. You get that just sudden jolt right there, and then it starts conducting. hopefully I made sense out of this. I mean, I'm not definitely not an expert, don't have a college degree, just do a lot of studying and reading because it's fun, but I could be saying things wrong, and if I am, please somebody correct me, because I really only want the right information out there, not just whatever sprouts out of my mouth. Hopefully you find this interesting. I mean, yeah, this little trainer board's cool. I like to have fun with this thing, but it's always constantly evolving, just like we all should be. We all should be evolving. If you're not trying to get better, what are you trying to do? And if I can find the instructions, I would be able to show you that this is a triac, just by the electrical symbol, which I think I will be able to. Oh yeah, there we go. Here's the instruction manual for this thing, and it lets you know right there. That is the symbol for a triac. So basically what these are thyristors. That's what they're called, is thyristors, right? They only conduct in one direction. And well, that only works great for DC, right? But this is AC. So how do you do AC? You have one forward biased, you have one reverse bias. Alternating current, right? Back, forth. Conducts in both directions, and that's how you are allowed to do AC with these. And that is, again, that is the symbol of a triac right there. Basically, so that little small line that you see there, that is the gate. So you have an anoid, a cathode, and a gate. Right? It's and if you've ever seen, like, especially if you work on like VRF and just other inverter driven equipment, these semiconductors, they use what is like NP or PN, which stands for positive negative. You'll see like an NPN, a PNP, which is positive negative positive, and they're just little small things that are just sandwiched together. And this is the semiconductor stuff. It takes the place of big, huge honking controls, you know. And it's, I mean, it's still the same crap, but they've just shrunk it down. That's really all it is. And this switch right here goes, activates, and so the triacs are a little bit interesting in their own right too, because they have a gate voltage, and that's what makes them conduct. And they will stay conducting even if you turn power off until you have dropped below the what they call the latching voltage, which keeps the gate open. You know, and however they're designed is how long the gate will stay open. So say you had one that it starts conducting at 50 milliamps and stops conducting at 30 milliamps. Well, even when you turn power off, you know, there's still voltage and current present, you know, and it will stay conducting until you hit the dropout voltage, and then that's when it'll stop conducting. If I'm speaking gibberish, I apologize, but just thought I would share. I mean, we could all learn some more stuff. I mean, I don't know if this would ever help any of you. I mean, again, I don't even know if it'll ever help me unless I'm trying to troubleshoot power electronics, which, you know, I mean, in its own right could be done and could be useful. And, you know, it's just, I look at it as it's another tool in the arsenal. It makes myself that much more valuable. Hence, you know, I'll have more work, get raises and things of that nature. I don't do it for those reasons. I do it just because I want to learn, and I am a how, what, why, when kind of person, you know. I mean, it's not good enough to know that You know, oh, cool. A light turns on, a light dims. Yay! I'm more like, how the hell does it do it? Because maybe one day having this knowledge will help me. Hope you're all having a good, nice, long Labor Day weekend. And happy HVACing.